Good day everyone, I am Desiree Angelique Rabuntin. You can call me Des and I will be the lecturer for the Earth Science class today. Please bear with my audio since I don't have a quality microphone. So let's start. To give us some insights, let us know what is Earth Science. Earth Science is the study of the Earth's structure, properties, processes, and 4.5 billion years of biotic evolution. Understanding this phenomena is essential to maintenance of the life on the planet. Let us now know all about Earth. Earth is basically our home planet and it is the third planet from the Sun. And it is the only place we know of so far that's inhabited by living things. Did you know that the name Earth is at least 1,000 years old? And all of the planets except for Earth were named after Greek and Roman gods and goddesses. However, the name Earth is a Germanic word which simply means the ground. Everything in Earth's system can be placed into one of the four major systems. And these are the land, water, living things, or air. These four subsystems are called spheres. Specifically, they are the lithosphere, which is the land, hydrosphere, which is the water, biosphere, where living things exist, and atmosphere, which is the air. Let us begin with the lithosphere. Lithosphere contains all of the cold, hard, solid land of the planet's crust or surface, the semi-solid land underneath the crust, and the liquid land near the center of the planet. The surface of the lithosphere is very uneven. There are high mountain ranges like the Rockies and Andes, huge plains or flat areas like those in Texas, Loa, and Brazil, and deep valleys along the ocean floor. The solid, semi-solid, and liquid land of the lithosphere form layers that are physically and chemically different. If someone were to cut through Earth to its centers, these layers would be revealed like the layers of an onion. The outermost layer of the lithosphere consists of loose soil, rich in nutrients, oxygen, and silicon. Beneath that layer lies a very thin, solid crust of oxygen and silicon. Let's now proceed to the second one, which is the hydrosphere. Hydrosphere contains all the solid, liquid, and gaseous water of the planet. It ranges from 10 to 20 kilometers in thickness. The hydrosphere extends from Earth's surface downward several kilometers into the lithosphere and upward about 12 kilometers into the atmosphere. A small portion of the water in the hydrosphere is fresh or non-salty. This water flows as precipitation from the atmosphere down to Earth's surface, as rivers and streams along Earth's surface, and as groundwater beneath Earth's surface. Most of Earth's fresh water, however, is frozen. 97% of Earth's water is salty. The salty water collects in deep valleys along Earth's surface. These large collections of salty water are referred to as oceans. The image above depicts the oh, water near poles is very cold while water near the equator is very warm. The differences in temperature cause water to change physical states. Extremely low temperatures, like those found at the poles cause water to freeze into a solid such as polar ice cap, a glacier, or an iceberg. Extremely high temperatures like those found at the equator cause water to evaporate into a gas. Second to the last is the biosphere. Biosphere includes both non-living elements such as sunlight and water, and living organisms. Biosphere is a term that encompasses all the ecosystems on Earth. Biosphere refers to the areas or the regions of the Earth possessing life. It is one of the distinguishing features of the Earth from other planets. The biosphere is part of the Earth that includes all biological communities and their environment. It is part of the Earth where life exists or we exist. And the last sphere of Earth that we are going to discuss is the atmosphere. It contains all the air in Earth's system. It extends from less than 1 meter below the planet's surface to more than 10,000 kilometers above the planet's surface. The upper portion of the atmosphere protects the organisms of the biosphere from the sun's ultraviolet radiation. It also absorbs and emits heat. When air temperature in the lower portion of this sphere changes, weather occurs. Excuse me. As the air in the lower atmosphere is heated or cooled, it moves around the planet. The result can be as simple as a breeze or as complex as a tornado. Gases in Earth's atmosphere, such as nitrogen and oxygen, are by far the most common. Dry air is composed of about 78% nitrogen and about 21% oxygen. Argon and carbon dioxide and many other gases are also present in much lower amounts. Each make up less than 1% of the atmosphere mixture of gases. The atmosphere also includes water vapor, and the amount of water vapor present varies a lot, but on average is around 1%. There are also many small particles, solid and liquids, floating in the atmosphere. These particles, which scientists call aerosols, include dust, spores, and pollen, salt from sea spray, volcanic ash, smoke, and more. We will now proceed to the layers of Earth's atmosphere. The first one that we have here is troposphere. The troposphere is the lowest layer of Earth's atmosphere. Most of the mass, about 75 to 80% of the atmosphere, is in the troposphere. Most types of clouds are found in the troposphere, and almost all weather occurs within this layer. The troposphere is by far the wettest layer of the atmosphere. All of the layers above contain very little moisture. The bottom of the troposphere is at Earth's surface. The troposphere extends upward to about 10 kilometers or 6.2 miles or about 33,000 feet above sea level. The height of the top of the troposphere varies with latitude, which is the lowest over the poles and highest at the equator. And by season, it is the lower in winter and higher in summer. It can be as high as 20 kilometers or 12 miles or 65,000 feet near the equator and as low as 7 kilometers or 4 miles or 23,000 feet over the poles in the winter. Air is the warmest at the bottom of the troposphere near ground level. Air gets colder as one rises through the troposphere. That's why the peaks of tall mountains can be snow-covered even in the summertime. Air pressure and the density of the air also decrease with altitude. That's why the cabins of high-flying jet aircraft are pressurized. The layer immediately above the troposphere is called the stratosphere. The boundary between the troposphere and the stratosphere is called tropopause. Sorry. Stratosphere is also the layer of Earth's atmosphere and is the second layer as you go upward. The troposphere, the lowest layer, is right below the stratosphere. The next higher layer above the stratosphere is the mesosphere, but first let us focus to the stratosphere. The bottom of the stratosphere is about 10 kilometers or 6.2 miles or about 33,000 feet above the ground and at middle latitudes. The top of the stratosphere occurs at an altitude of 50 kilometers or 31 miles. The height of the bottom of the stratosphere varies with latitude and with the seasons. The lower boundary of the stratosphere can be as high as 20 kilometers or 12 miles or 65,000 feet near the equator and as low as 7 kilometers or 4 miles or 23,000 feet at the poles in the winter. The lower boundary of the stratosphere is called the tropopause. The upper boundary is called the stratopause. Ozone, an unusual type of oxygen molecule that is relatively abundant in the stratosphere, heats this layer as it absorbs energy from incoming ultraviolet radiation from the sun. Temperatures rise as one moves upward through the stratosphere. This is exactly the opposite of the behavior of the troposphere in which we live, where temperatures drop with increasing altitude. Because of this temperature stratification, there is little convection and mixing in the stratosphere, so the layers of air there are quite stable. Commercial jet aircraft fly in the lower stratosphere to avoid the turbulence which is common in the troposphere. The stratosphere is very dry. The air there contains a little water vapor. Because of this, few clouds are found in this layer. Almost all clouds occur in the lower, more humid troposphere. Polar stratospheric clouds or PSCs are the exception. PSCs appear in the lower stratosphere near the poles in the winter. They are found at altitudes of 15 to 25 kilometers or 9.3 to 15.5 miles and form only when temperatures at those heights dip below -78 degrees Celsius. They appear to help cause the formation of the infamous holes in the ozone layer by encouraging certain chemical reactions that destroy ozone. PCs are also called nacreous clouds. Air is roughly 1,000 times thinner at the top of the stratosphere than it is at sea level. Because of this, jet aircraft and weather balloons reach their maximum operational altitudes within the stratosphere. Due to the lack of vertical convection in the stratosphere, materials that get into the stratosphere can stay there for long times, such as the case the ozone-destroying chemicals called CFCs, chlorofluorocarbons, large volcanic eruptions, and major meteorite impacts can fling particles up into the stratosphere where they may linger for months or years, sometimes altering Earth's global climate. Rocket launches inject exhaust gases into the stratosphere, producing uncertain consequences. Various types of waves and tides in the atmosphere influence the stratosphere. Some of these waves and tides carry energy from the troposphere upward into the stratosphere. Others convey energy from the stratosphere up into the mesosphere. The waves and tides influence the flows of air in the stratosphere and can also cause regional heating of this layer of the atmosphere. A rare type of electrical discharge, somewhat to lightning, occurs in the stratosphere. These blue jets appear above thunderstorms and extend from the bottom of the stratosphere up to altitudes of 40 or 50 kilometers or 25 to 31 miles. Let's now proceed to the third one, which is the mesosphere. Mm, The mesosphere is directly above the stratosphere and below the thermosphere. It extends from about 50 to 85 kilometers or 31 to 53 miles above our planet. Temperature decreases with height throughout the mesosphere. The coldest temperature in Earth's atmosphere, about -90 degrees Celsius or -130 degrees Fahrenheit, are found near the top of this layer. The boundary between the mesosphere and thermosphere above is called menopause. At the bottom of the mesosphere is called the stratopause, the boundary between the mesosphere and the stratosphere below. The mesosphere is difficult to study, so less is known about this layer of the atmosphere than other layers. Weather balloons and other aircraft cannot fly enough to reach the mesosphere. Satellites orbit above the mesosphere and cannot directly measure the tides of this layer. Scientists use instruments on sounding rockets to sample the mesosphere directly, but such flights are brief and infrequent, since it is difficult to take measurements of the mesosphere directly using instruments such about the mesosphere is still mysterious. Most meteors vaporize in the mesosphere. Some materials from meteors lingers in the mesosphere, causing this layer to have a relatively high concentration of iron and other metal atoms. Very strange high-altitude clouds called noctilucent clouds or polar mesospheric clouds in the mesosphere near the poles. These peculiar these peculiar clouds from much higher up than other types of clouds. The mesosphere, like the stratosphere below, is much drier than the most troposphere we live in, making the formation of clouds in these layers a bit of a surprise. Odd electrical and discharges akin to lightning called sprites and elves occasionally appear in the mesosphere thousands of kilometers or miles above thunderclouds in the troposphere below. The stratosphere and mesosphere together are sometimes referred to as the middle atmosphere. At the menopause or the top of the mesosphere and below, gases made of different types of atoms and molecules are truly mixed by the turbulence in the atmosphere. Above the mesosphere, in the thermosphere and beyond, gas particles collide so frequently that the gases become somewhat separated based on the types of chemical elements they contain. Various types of waves and tide in the atmosphere influence the mesosphere. These waves and tides carry energy from the troposphere and the stratosphere upward into the mesosphere, driving most of its global circulation. Second to the last is the thermosphere. It is a layer of Earth's atmosphere. The thermosphere is directly above the mesosphere and below the exosphere. It extends from about 90 kilometers or 56 miles to between 500 and 1,000 kilometers or 311 to 621 miles above our planet. Temperatures climb sharply in the lower thermosphere below 200 to 300 kilometers altitude, then level off and hold fairly steady with increasing altitude above the height. Solar activity strongly influences temperature in the thermosphere. The thermosphere is typically about 200 degrees Celsius or 360 degrees Fahrenheit hotter in the daytime than at night, and roughly 500 degrees Celsius and 900 degrees Fahrenheit hotter when the sun is very active than at other times. Temperatures in the upper thermosphere can range from about 500 degrees Celsius or 932 degrees Fahrenheit to 2000 degrees Celsius or 3632 Fahrenheit. 3632 degrees Fahrenheit or higher. The boundary between the thermosphere and the exosphere above it is called the thermopause. At the bottom of the thermosphere is the mesopause, the boundary between the thermosphere and the mesosphere below. Although the thermosphere is considered part of the Earth's atmosphere, the air density is so low in this layer that most of the thermosphere is what we normally think of as outer space. Outer space. The most common definition says that space begins at an altitude of 100 kilometers or 62 miles, slightly above the mesopause at the bottom of the thermosphere. The Space Shuttle and the International Space Station both orbit Earth within the thermosphere. Below the thermosphere, gases made of different types of atoms and molecules are thoroughly mixed ones in the atmosphere. Air in the lower atmosphere is mainly composed of the familiar blend of 80% nitrogen molecules and 20% oxygen molecules. Sorry, and about 20% oxygen molecules. In the thermosphere and above, gas particles collide so infrequently that the gases become somewhat separated based on the types of chemical elements they contain. Finally, the aurora, or the southern and northern lights, primarily occur in the thermosphere. Charged particles or electrons, protons, and other ions from space collide with atoms and molecules in the thermosphere at high latitudes, exciting them into higher energy states. Those atoms and molecules shed this excess energy by emitting photons of light, which we see as colorful auroral displays. Let's proceed to the last layer of the atmosphere, which is the exosphere, which is the uppermost region of Earth's atmosphere as it gradually fades into the vacuum of space. The air in the exosphere is extremely thin in many ways. It is almost the same as the airless void of outer space. The layer directly below the exosphere is the thermosphere. The boundary between the two is called the thermopause. The bottom of the exosphere is also called refers to as the exposés. The altitude of the lower boundary of the exosphere varies. When the sun is active around the peak of the sunspot cycle, X-rays and ultraviolet radiation from the sun heat and puff up the thermosphere, raising the altitude of the thermopause to heights around 1,000 kilometers or 620 miles above Earth's surface. When the sun is less active during the low point of the sunspot cycle, solar radiation is less intense and the thermopause recedes to within about 500 kilometers or 310 miles of Earth's surface. Not Not all scientists agree that the exosphere is a part of the atmosphere. Some scientists consider the thermosphere the support of Earth's atmosphere and think that the exosphere is just part of space. However, the scientists do consider the exosphere part of our planet's atmosphere. Since the exosphere gradually fades into outer space, there is no clear upper boundary of this layer. One definition of the outermost limit of the exosphere places in the uppermost edge of Earth's atmosphere around 190,000 kilometers or 120,000 miles, about halfway to the Moon. At this distance, radiation pressure from the sunlight exerts more force on hydrogen atoms than does the pull of Earth's gravity. A faint glow of ultraviolet radiation scattered by hydrogen atoms in the uppermost atmosphere has been detected at the heights of 100,000 kilometers or 62,000 miles by satellites. This region of UV glow is called geocorona. Before we proceed to our next topic, let us first recall our previous topic. The first one mm, we have Earth's sphere, which is the lithosphere, which is the land, hydrosphere, which is the water, biosphere, which where living organisms exist, and lastly, the atmosphere, where where air exists, and also the layers of the atmosphere, which is the troposphere, the first one, where we can see the clouds. The second one is the stratosphere, that's where we can see the ozone layer. The third one is the mesosphere, where we can see meteors and comets. The fourth one is the thermosphere, where we can see the aurora borealis. And the last one, which is the exosphere, where we can see spacecrafts, spaceships, and some aircrafts. Let's now proceed to the next topic, which is the Earth's layer. Temperatures deep inside the Earth can range from 4,000 to 6,000 degrees Celsius. That is as hot as the sun. Because of such immense pressure, rocks remain solids and liquids instead of turning into gases. Only 50 kilometers or 30 miles beneath the surface, it is already almost 1,000 degrees Fahrenheit. It also has a pressure of 200,000 psi or pressure per square inch. Bike tires are about 35 psi. The temperatures increase as you go deeper into the Earth, with the lithosphere comprised of the crust and upper mantle being the coolest, averaging about 300 to 500 degrees Celsius. The asthenosphere is the next layer, averaging about 1,300 degrees Celsius, making it slightly more fluid than the lithosphere above it. It transitions into the place called the moho or moho-rhombic discontinuity, or the point between the crust and the mantle below. The upper mantle is much stronger than the asthenosphere at about 500 to 900 degrees Celsius, and the lower mantle is denser and hotter, reaching temperatures over 4,000 degrees Celsius. And finally, the core is the hottest at about 5,000 degrees Celsius, being the most gooey of the layers. I'm sorry, I forgot to switch the slide. Yeah, that's how Earth's layer looks like. Next is composition. Each layer has a distinct set of rocks and minerals that make it unique. However, they all contain some of the same things such as iron. Despite their similarities, the differences in composition are what define the layers, causing them to be distinct. Earth's crust is much like a skin consisting of two types, oceanic and continental. Oceanic crust is mainly basalt with limestone, serpentine, and clay. Continental crust contain of mostly granite and some quartz. The upper mantle is thought to contain rocks such as olivine, peridotite, and garnet. These shift at the moho because of high pressure and are replaced by more stable minerals such as perovskite. The rest of the mantle consists of other iron-rich rocks. The core is divided into the outer and inner core because of the distinctions between the state of iron at the depths. The outer core is liquid iron, flowing plastically. The inner core, however, is solid because of such extreme pressure. Earth's crust is about 6 to 35 kilometers or 4 to 21 miles thick. The mantle the mantle layer formed from rapidly flowing magma, and it is about 2,900 kilometers or 1,800 miles. The thick outer core containing such molten heavy metals as nickel and iron is about 2,000 kilometers or 1,450 miles, and lastly, the inner core, which is in the crystalline state because of the influence of heat and high pressure, is about 1,370 kilometers or 851 miles. Crust. The lithosphere consists of the crust and the upper mantle. As we read before, crust can be divided into two different types, continental and oceanic crust. Both types float on the denser mantle. Continental crust is about 25 to 90 kilometers or 15 to 55 miles thick and divided into tectonic plates. These plates move slowly, just a few centimeters, each year over the more fluid mantle. The tectonic plates make up distinct regions of the Earth's surface, such as continents. Oceanic crust, which is much thinner than continental crust, is at only 6 to 11 kilometers or 3 to 6 miles thick, and it is where new crust is formed. This can happen by two plates moving apart and the magma from the asthenosphere coming up and cooling to form new seafloor. Next is the asthenosphere. It is more fluid than the rigid lithosphere above it. Like with the plastic-like texture, this is due to the increased temperature and pressure that rocks experience as they descend into the asthenosphere from the lithosphere, making them molten. The molten nature of the asthenosphere makes it possible for plate tectonics to happen. If the plates were not able to shift on the semi-liquid region, then new mountains would not form, and the theory of Pangaea, the supercontinent of 300 miles years ago, would not exist. Mountains are formed when two plates converge and flow towards each other, and possibly even cause of asthenospheric material to flow up through causing a volcano. Asthenospheric material can also escape the surface when plates move away from each other or diverge. The asthenosphere is the supplier of new material for the lithosphere and replaces the lithospheric material as it cycles through. We moved from the asthenosphere into the upper mantle through the Moho-Rivisic discontinuity or the Moho. The Moho is characterized by a drastic increase in seismic rate, discovered by Andrija Mohorovic in 1909. The upper mantle is fairly plastic relative to the layers above it. Not much is known about the seismic activity of the lower mantle, but scientists assume that it is relatively consistent since the mantle is molten. Flowing freely, it has convection similar to those that occur when boiling water on the stove. The magma heats as it gets closer to the core and rises closer to the asthenosphere, cooling as it gets closer and falling again to be heated and rising again, continuously cycling. Last one is the core. The core is something that scientists can only make hypotheses about because it is so deep in the earth that no instrument could make it that far down. Even if it was long enough, the temperature the temperatures and pressure are so extreme that anything would be destroyed before any data was accumulated. What we do know is that there are two parts, an outer core and an inner core. The outer core is the liquid iron alloy at extremely high temperatures flowing molten, and the inner core is thought to be solid iron and has been thought to be pure iron for many years until recently. Scientists have been studying the core's density and testing it if a lighter element may be present in addition. So mainly, the Earth's layer is only three, which is the crust, mantle, and core. But if you um, expand the layers of Earth, you will get the lithosphere, asthenosphere, upper mantle, lower mantle, outer core, and inner core. And that concludes our Earth Science class. Now, I will send a link for the quiz that you will take to determine if you learned something from this lesson. That's all for our Earth Science class. See you next week for more learnings. Thank you.
Thank you everyone. Pwede po kayong mag-leave na. And then you can answer the quiz na nasa chat. And nasa provided din po yung materials sa Google Classroom. So, be back na lang by before 4 para sa next class natin. Thank you.